Right. Today we'll be talking about binary tree and the representation. Have you ever wondered, you're writing in a form of a tree? Everything you're writing in a form of a tree, and we have learned so many trees so far. We have seen the traversals, we have seen binary search tree, we have seen many things. But my question is, are they internally represented in the computer this way? No, these are non-linear data structures, right? Trees are non-linear data structures. So, are they represented internally in the computer like this, or is there any other representation? Okay. The question is, the answer is yes, there are two kinds of representation for a binary tree. The one representation is node representation of a binary tree. Okay. And the other thing is implicit array representation. We'll be talking about these two in this video. Okay. This is very, very important. If you want to learn heaps, then you should definitely know this implicit array representation. Okay. So anyway, we'll study both of them now. In the at first, you'll study about node representation. Okay. So what is the node representation? As you know, node representation is nothing but we implement by using a double linked list. I think you have studied about double linked list. We had a video of a double linked list in linked list folder playlist, so you can go there and watch about double linked list. But for this concept, I think you need not have that. Okay, so what is a double linked list? You'll have a data. You'll have a right pointer as well as a left pointer. Okay, so the nodes can traverse either this way or they can have this way. So both of them can be traversed like that. Okay. So how is it represented? See here, struct node in data. Okay. And struct node, this is a left pointer and this is a right pointer. That is how it is represented. Okay. So what I'll do is I'll take a tree and I'll show you how it is represented inside a computer. Okay. Okay. Here you can see there is a tree here. There is a small tree I have taken. 10, the left node of 10 is 5 and right node is 20. Okay. And similarly 5, we have left node as 3 and right node as 7. Okay. So we'll represent it now. See here. Now 10 is the data. Okay. We have 10 as the data. Okay. And we have this left pointer and this is the right pointer. And to the left pointer, we have 5 as the data, isn't it? If you could visually see that to the left of 10, we have 5. So 5 as the data. And of course, this is also a linked list. So it will also have a left pointer and the right pointer. Okay. And 10 to the right of 10, what is that we have? We have 20. Okay. So we have 20. And 20 will also have the left pointer and the right pointer. Okay. Right. To the left of 20 or right of 20, we don't have anything. So we are not representing anything. Okay. But to the left of 5, we have 3. To the right of 5, we have 7. So we'll represent here. To the left of 5, we'll have 3. And to the right of 5, we'll have 7. This is how internally a tree is represented. Okay. Although we show it like this, but internally, this is how it is represented. Okay, this is called node representation of a binary tree. Okay, I hope you have understood the difference. You have understood the concept rather. Okay, right. Let us talk about what are the advantages and disadvantages of this kind of representation. Okay, so one advantage we have is dynamic size. So we need not explicitly mention that the tree is of length so and so. Okay, let us say no, we have studied about height, right? So we need not explicitly or mention that the height of the tree would be definitely 10 or definitely 100. No, we need not mention. As and when the size increases or the height increases, either the height or the width, anything increases, the linked list will appropriately expand its size. Okay, we've already seen the difference between arrays and linked list, where we have seen that linked list will offer you dynamic size allocation or dynamic memory allocation. Okay, right. And ease of insertion and deletion, yes, insertion is quite easy because you could see if you have a left, if you have a tree, if you have a node in the left side, you just insert the node, and if you want to delete, you just straight away delete. Okay, so there is no much deal in the case of insertion and deletion. And efficiency for sparse trees, yeah, we'll study about what are sparse trees and what are dense trees just a moment after explaining both implicit as well as this node representation. I'll be explaining that also. Okay, so yeah, this what are the disadvantages? Extra memory needed for the pointers, of course. Everything, you for every node we have the left pointer and the right pointer, isn't it? For every node we have both of them. Okay, let us say if you have 1000 nodes, let us say the node, the tree is having 1000 nodes, then how many pointers are needed? 1000 into 2, that is 2000 pointers are needed. Why 2? Because we have left and right pointer. So each pointer, let us say it will take 4 bytes. So what is it? So it is around 8000 bytes, so which is a lot of memory that is wasted. Okay, so that is what they are pointing it out. Okay, traversal is slightly slower than arrays, definitely, because if you see, we'll study about array representation as well, but just understand, arrays, how they work, right? So let us say if I have an array like this, and if I have the numbers, let us say 1, 2, 8, 9, 6, 7. Now the indices are 0, 1, 2, 3, 4, and 5. So if I have to access 9, definitely I can say A of 3, simple. It is accessed. But in the case of a linked list here, in the case of a linked list, if I want to access 7, if I want to access 7, then I have to access 10, then I have to access 5, then I can access 7. There is no direct access. There is a sequential access, but not direct access. So that's the reason they are telling that in the case of node representation, traversal is slightly slower, definitely slower. Okay, right. Right. We'll go forward to the implicit array representation. Okay, this is implicit array representation. Okay, so we'll have a tree now. We'll just have a tree. Let us say this is A, B, C, D, and E. Okay, and also let us say F. Now, these are the rules for indexing. Okay, so what we'll do is we'll have an array as well. I hope the space is sufficient. Okay, array indices start from 1. So yeah, array indices start from 1, 1, 2, 3, 4, 5, 6, and 7. Right. Okay, if you need, we'll expand. Anyway, so right, what they're saying, if a node is starting at index I, the left index is 2i and the right is 2i plus 1. Okay, let us say the indices start from 1. That is what I've mentioned here. You could see. Now, what they're saying is left index is 2i. That is, this index is 2, 2 into i. That is, I is 1 now. Okay, I is 1. So, what is 2i? If I is 1, then it is 2. What is 2i plus 1? 2 into 1 plus 1, which is nothing but 3. That is how it is represented. Now, here A is represented in 1, okay, B is represented in second location, and C is represented in the third location. That's it. Okay. Now, what about the next, these nodes? For these nodes, the I will be this, because the parent of this node is the DNA is B. So we'll take I as this. Now, what is this? This is nothing but 2i, which is 2 into I is now 2. So this will be 4, isn't it? Okay. What about this 2i plus 1? The right node is 2i plus 1. You could see here. Okay. So I is now 2 because this is E, for E parent is B, and the index of B is 2. So 2 into 2 plus 1, which is nothing but 5. Okay. Now the placement of D is 4 and the placement of E is 5. Can you just pause the video and tell me what is the index of F? Try to tell me what is the index of F. Just pause the video. Okay. So for F, it is just simply 2 into I, because I is 3 here. It is simply X, 6, sorry. So this is F, right? So this is how a implicit array is represented. Okay. If you are studying heaps, we have a video on heap sort and heaps. If you see here, that works on this principle. Heap sort works on this principle. You just go through that video, you'll probably understand that. Okay. Right. This is how implicit array is represented. Now let us also examine the advantages and disadvantages of this approach. Yeah, obviously the first advantage is no pointers are required because we are not using any pointers here. Okay. And faster accessing using formulas. Yes, I have told you, because if you want to access, if I want to access, let us say D, now I can simply tell you that it is A of 4. Then what is the answer I'll get? I'll get D straight away. Okay. So very faster access. Efficient for complete tree. What is a complete tree? If any tree, every tree, I have already made a video. Okay. For example, this is a complete tree. It is efficient for complete tree. Okay. What is a complete tree? Every node will have either 0 or 2 nodes, and it is you know left to right. It will be filled left to right. So first the left node will be filled, then the right node, then again the left node, and then again the right node, and then left node and right node. Okay. Anyway, I have made a video of it about what are the types of trees. So you just go through that video. So for complete trees, it is very, very efficient. Okay. So no pointers are required, faster access using formulas, and efficient for complete trees, sorry. Okay. Right. Disadvantage is wastage of memory for sparse trees. What are sparse trees? I'll explain. Okay. Fixed size in many implementation, because here you have to represent whether how many arrays. What is the array size? You have to mention. You have to mention, let us say A of 100 or A of 1000, or you have to mention the size, and your tree is limited by the size of array. Common sense, right? Okay. Because if you have already mentioned 100, then you can only have a node less than 100. Okay. Okay. Anyway, if it indexes from 1, you can have up to 100 nodes. Okay. Right. So difficulty in insertion and deletion. Yes, it is difficult, because if you want to insert the 100th node, you have to go through, right? Let us say, if you want to insert the 100th node, you have to go through each and every node, because if you see simply, if you have to insert this node here, if you want to insert this node, what we are doing, we have to calculate this, we have to calculate this, we have to calculate this, and then we have to calculate this and calculate this, and then calculate this, and then after that you can calculate this. Imagine if you want to calculate for the 100th node, what will happen? You have to calculate all the 99th nodes index, and then you can calculate the 100th node. So difficulty in insertion and deletion, because you have to calculate for every node what is the array position. So that is what it is difficult. Okay. Right. So these are the disadvantages. So okay, as I told you, I'll explain about sparse trees. Okay, what is a sparse tree and what is a dense tree? See, let us say you have a tree like this: A, B, C, and D. This is one kind of a sparse tree. This is one kind of a sparse tree. Okay. Whereas what is a dense tree? Say a normal tree like A, B, C, D, E, F, and G, like normal tree. Okay. Right. Just pause the video and tell me which tree can be used for which representation. Like sparse tree, is it better if you do it with node representation, or the implicit array representation, which is better for the sparse tree, which is better. Just pause the video and you just analyze which is better. If you want to take a sparse tree and represent it using an array, okay, how will it happen? Let us say the index is 1. Okay, now the left index will be 2 into I, which is nothing but 2. Okay, now what is the index for this? 2 into 2, which is nothing but 4. For this, 4 into 2, 8, because we know the left index is 2i. Okay, so if you want to represent here, see what will happen is, I think I don't have a space here, so see, if you want to represent here, see what will happen. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now 2 can be represented, 1 can be, A can be represented here and B is represented here. So far so good, but C is represented at 4 and D is represented as 8. So don't you think these are waste? This is a waste, this is a waste, this is a waste, this is a waste. Okay, so how many bytes you're wasting? Essentially, let us say 2 bytes each. So this is 1, 2, 3, 4. You are using 8 bytes and you're wasting 8 bytes. Okay, so for a sparse tree, which is better? Of course, that is the node representation, because in a node representation, you can simply represent like this: A, B, C, and D. You can easily represent it like this. Okay, so for a sparse tree, node representation is better. Okay, what about a dense tree? If you want to represent a dense tree, the better representation is definitely implicit array representation, because if you see here, we have already done this. So let us say this is 1, this is 2, this will be 3, this will be 4, 5, 6, 7. Okay, so we can happily accommodate all of them in a order. Though no memory would be wasted here, because A can be represented here, B can be represented here, C, D, E, F, G. All can be represented happily. But if you use the node representation, what is the problem? You will have to use a lot of pointers. You'll have to use a lot of pointers, because for every node we'll have left and the right pointer, we have discussed in the earlier case. So that's the reason, that is the difference we'll have. So in essence, finally, the summary is, for a sparse tree, you better use the node representation, and for a dense tree, you better use the implicit array representation. Okay, so right, so let us go forward and see what are the previous questions that were answered, that were given on this concept. So they were given you a 6-mark question: explain the concept of binary representation and discuss the node representation and implicit array representation. My recommendation is you just pause this video and again listen to this video again, and you make a notes of yourself, so that you can answer this question very, very easily. Okay, so if you follow these videos completely, you should be able to answer any question in the exam. Okay, right. I hope you understood everything that I've explained today. Okay, thank you so much. We are going to continue with our next videos.